So just watch the time. I told you guys yesterday we were going to have a work day either Friday or Monday. I've clearly decided on Monday. I'll also do a homework check that day. Don't forget about the due dates. Those haven't changed. But you now have another work day before both of those are due because it's midnight. So you had a work day basically on Monday. You have another one on Friday. No excuses for not getting these 2 items done. So if you want to plan on working on your quiz in class with classmates on that day, totally fine. Up to you. Remember, I can't help you, but you can help each other. Okay. And so what I love about this lesson today, guys, is that it reviews a lot of what's on your quiz. Inverses, rewriting logs in their other form, things like that. Okay, so even though this section in particular is not on your quiz, it does review very nicely what is on your quiz. And so the homework's very short. I don't think anyone struggled with anything today, but there's a ton of great review in this, so really pay attention, stay awake, stay focused, all that stuff. Okay, so what unit or section 10 today and tomorrow is all about is inverses of exponential functions. So you might remember exponential functions were those, right? And they made like a J, and we'll be graphing them again today. And if you remember what inverses are, it's switch the x and y's. Inverses are switch x and y, and if it's in an equation, you would solve for y again. Fun fact is the inverse of an exponential function is a log function. Okay, so exponential functions and log functions are inverses of each other. Okay, and we just started working with logs yesterday. Today we're going to graph, well, right away, right in the beginning, we're going to graph an exponential function and its inverse. So in example 1, there's a table of values already created for us. You have to love pre-printed notes. I mean, come on, these are nice. Already created for us. And you haven't learned how to do this yet. I will show you in the next example or 2 examples how to find the inverse, switch x and y and solve for y. So that's a big part of what we're doing today. But in this one, it's already done for us. We're just looking at the graphing. So let's start with just this XY chart. So these are the X values that we typically plug in, and we plug in here and make a table of values. And if you remember, I like to start with 0. So 2 to the anything to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4. And then remember, if we know the positive 1 is 2, the negative 1 is not negative 2, but 1/2. Not negative, right? We just flip it. And then positive 2 is 4, negative 2 is 1/4. Okay? So let's just go ahead and graph f of x, those points, just an easy sketch, no stress. To the left 2, up a little bit more. There's my y-intercept of 0, 1, 1, 2, and 2, 4. Fine, right? And you might remember that in an exponential function, the points get really, really, really close to something called an asymptote and never touch it. And so you can see we're getting really, really close to 0, right? We will have an asymptote right here. Knowing where the asymptote is helps us with those last few points. We know what's happening here, right? As we go to the right, it's going up. As we go to the left, we're getting really, really close to our asymptote, but we're not going to touch it. So that's the graph of f of x. Done. Now, switch gears. Oh, by the way, let me just write this. You have a horizontal asymptote in exponential functions, and in this problem, it's y equals 0. Remember H-A-Y, hey, horizontal lines are y equals something. Okay, so there's that. Now, let's switch gears and look at the inverse. Remember, this is the symbol for inverse. This log base 2 of x is the inverse of this, and I'll prove it to you algebraically later. But for right now, let's just graph this graph. And guess what? All we have to do is remember that in an inverse, the x's and y's switch. So I don't actually have to plug and chug the same numbers. I know that if these are inverses, and they are, that I can just flip the xy chart. So my x's of f of x are now the y values of f inverse of x. And vice versa. Go ahead and write the other one here. Awesome. All right, so I'm going to have 1/4, 1/2, and so on all the way down. Haley, you can sit in Jocelyn and Chase's seats if you don't mind. That way you guys can sit together. Okay, so guys, here we have the points. Let's graph them. So this is to the right, positive 1/4, down 2, down 1. We have an intercept on the x-axis this time. 2, 1, we're on page 115, you guys, and 4, 2. So look, you can see what's happening here, right? You can see it's going like this. We're pretty confident about what's happening here. But what's happening here is we're going to be getting really, really close to another asymptote. Right here. So in a log function, we have a VA, a vertical asymptote of x equals 0. Okay? And it has the same behavior near the asymptote as the exponential function does. As we approach our asymptotes, we get super, super close in teeny tiny numbers, but we never cross and we never touch it. Never touch it, never cross it. Okay? We just graphed the exponential function. We just graphed the log function. What is this? This is called the identity function, y equals x. That's a line with a y-intercept of 0 and a slope of 1. It's right here. It goes right through the middle. What this graph is here, let me be a proper math teacher and put all my labels. Okay, so there's my inverse, there's my function. Remember I said they are inverses of each other, and they do have like this similarity, right? Especially if I could graph really nicely by hand. But what y equals x is, the identity function, that is your line of symmetry between any two inverses. So if you graph a function and you graph its inverse, it doesn't have to be these two, it could be any two graphs, okay? They will always be symmetrical over the identity function, which is y equals x. Just a fun fact. So if I folded my paper on that green dotted line and I graphed it perfectly, all the points would line up. That's a line of symmetry between them, okay? All right. Now, in example 2, it tells us to graph y equals log base 2 of x. Well, that's what we just graphed right here. Okay, it's the same graph, but we're gonna do it a lot nicer and we're gonna dissect it. But we're gonna use our graphing calculator to do it this time. A couple things I want to say. Look ahead of what we're having to answer in this example. Domain, range. This is your end behavior, by the way. Limit functions, asymptote, intercept, concavity. We have seen these features of graphs over and over and over again. That must mean they're really important, okay? Every time I introduce a new function to you and we graph it, we break it down, we tear it apart, we move it all over the place, we always talk about this stuff. Because guess what? Tomorrow is taking log functions and doing our left, right, up, down, stretch, shrink, flip, all the stuff that we've done a million times comes back tomorrow. And so here's this stuff again. So another thing before I graph it, I want to show you. Yesterday, if you remember, I showed you how to find the button where you can put a log with a non-base 10 in. And if you remember, that was math. We went up 2 to A. Fine. Still works great. But I do have a shortcut one for you, and that's math alpha math. It's good to know more than one way of doing things, right? Math alpha math is a little faster. Use what you want. There's actually 2 other ways that I'm not even going to bother to show you a whole bunch of ways. But math, the button right above it, math gives you that same thing. So you decide what makes you happy. So clear your RAM for me, please. And let's put this function in our calculator. I need to clean my screen. I write on it too much. Okay, so I'm going to use math alpha math to put that log thingy in there. I can put my 2 in there and then an x in there. And let's graph it, see what it looks like. And we knew what it looked like, right? We already graphed it. Graphed it right there. Evan, take your headphones off for me, please. Okay, so I'll wait. Make sure he gets on there. Go to y equals math and alpha math. All right, let's go to the table of values. Guys, let your calculator do the work for you. We're going to pick points, okay? Pick nice points. Pick points that are easy to graph. Like 1, 0 is an easy point to graph, right? 2, 1 is an easy point to graph. And I don't like that other one. Let me go down. 4, 2 is nice. And let's maybe pick one more just to really round out the shape. 8, 3. I don't need those decimally ones in between because remember, this is a continuous graph. So we hit all those decimals in between. But what's happening over here, okay? Well, what's really nice about logs, in your calculator, in your table, you can find your asymptote. It's where your first error is. Because we had a really good point at 1, 0, and then between 0 and 1, something changed, right? Once we get to 0, there's an error because that's your asymptote, right? We have an asymptote right here. And if you keep scrolling up, you'll see it's just error forever. Why? Because we can't go over there. None of those points are part of our graph. And once we know where our asymptote is, guys, we can finish the graph because we know that the behavior of a graph near its asymptote is that it gets really close to it and then just continues on. And that's an easy way of finishing the graph. Okay? Now, we are still making mistakes. We've talked about this before with domain and range on tests and stuff. We can't just memorize. If you just try to memorize, there's too many graphs that we work with and too many things that happen in flipping and then they stretch and they shrink and they move up. To try to memorize domains and ranges with different types of functions isn't going to work. The easiest way is from the picture, and we have a picture. So look at the graph. Domain is your x values. What is the domain of this graph? Somebody want to try it? Yes, Jocelyn. Jocelyn said it first. 0, I shouldn't have put the parentheses already. I was going to ask her. But 0, right, to positive infinity. Those are the x values we use. Not 0, though, right? At 0, we have an error because of the asymptote. But by using parentheses, we're excluding the 0 and including anything to the right of the 0. Make sense? 0 to infinity. Evan, you see it? Evan, can you tell me the range? Can you tell the range? Am I looking at it? Help them out, somebody. Range. All real numbers, negative infinity to infinity. That's right. Look. It goes down forever. Nothing is stopping this curve from going down. There's something stopping it from going to the left, but going down, fine. And as it goes to the right, there's nothing that's going to stop it from going up forever. Those arrows are free to go down and up forever. So negative infinity to infinity. Yes? Sure. Right. You mean like because of that? Yeah. That's right. Because at -1, at -2, that's these numbers. It says error. So those are not part of the graph.
But what about geometry? I'm talking about the y-axis.
There are. Do you know where they are? Okay. That is I have never had a student ask that question. Really good question. Does anyone know how to answer her question? Listen to what she said. There's no y values that have negatives on here. But our graph does, right? These are all negative. Where are my negative y values? In between 1 and 0. Look. Between 0 and 1, right? That is where all my negatives are. Where are they? Well, we have our calculator default set to count by ones. What if I put in something really tiny, like 0.001s or something? That means every number is going to change by that. Please work. Yep, there's my negatives between 0 and 1. Okay? So without having to take a bunch of time to do something like this, and it's fine, you can, but you're timed in these tests and stuff like that. We just kind of know, okay, if I have a good point at 1, 0, and I have an asymptote at 0, that means that is my asymptote, and between 1 and 0, I'm just going to get as close as I can, in that case, into the negatives. Good question. All right, end behavior. As the limit of this graph as x approaches positive infinity. What are my y values going to do? Infinity. They're going up, 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 right? Now look at this one. We haven't seen this limit statement in a while. The limit of the graph as x approaches 0. What's that plus mean? From the right. What is happening as my x's get closer to 0 from the right? You can't get to 0 from the left, and you can't go to negative. Normally we see negative infinity right there. Why doesn't it say as x approaches negative infinity? Because x isn't approaching negative infinity. It can't go there. You're being stopped. So it's only approaching 0, and it's only approaching 0 from the right. What are the y values doing now? They're going down. Okay? We'll see that again in another problem. We just talked about this asymptote already. We have a vertical asymptote at x equals 0. You have to put the x. You can't just put 0. Okay? We have an intercept at 1, 0, right? Intercept can be x or y. This one happens to be on the x-axis. And is this one concave up or down? Down. A fun fact also is that is this graph increasing or decreasing? It's increasing. Listen to what I'm about to tell you. Whenever your base of a log is greater than 1, it's going to be increasing. I said that same thing to you with an exponential function. When the base is greater than 1, the graph is increasing. So guess what happens? In our next problem, our base will be less than 1, and our graph will be decreasing. So we're going to do the same thing with another one. Yeah. Yeah, okay. I'm recording. All right, let's put this guy in our calculator. Math alpha math. You can put 1/2 or 0.5. 0.5 is a equivalent of 1/2. Let's see what it looks like just to get an idea. Okay, got it. Then go to your table. 0.5, put 0.5, and then x. Go to your table, and let's pick some good points. 1, 0 looks good. 2, -1 is a nice point. Let's skip all those yucky numbers. Go to 8, -3. Did I miss one in there? Oh yeah, 4, -2. So I just picked some nice, easy numbers to graph. Okay, let's find our asymptote. There it is at 0 again. So once I know where my asymptote is, I can finish the other half of the graph, right? So we know it's going to keep, there's nothing stopping it from going here, and then it's just going to keep approaching that asymptote, and that looks like the graph, right? Looks like it. Okay, domain. Same as last one, right? 0 to infinity. 0 to infinity, not including the 0. Remember, brackets and parentheses are a big deal. We have to know when to use them. How about the range? It is all real numbers. We go up forever, we go down forever. Remember, always least to greatest when you write it. Here's our end behavior again. As our graph, no, careful, look at the graph. You can't just say, oh, on the last one it was this, so it's going to be that again. Look at the graph. It changes. That's why we have to understand it. As the graph goes to the right, what are my y values heading towards? Negative infinity. They're going down. My y values are getting smaller as my x values are getting bigger. Right? As my x values get bigger, my y values get smaller. How about as I approach 0 from the right? What are my y values doing? Positive. They're going up, right? Positive infinity. We have that vertical asymptote. It's a vertical line, right? Vertical vax, V-A-X, to help you remember. Vertical is x. We have that intercept at 1, 0, right there. And this one is concave up, right? It would hold water. And remember how I told you, if your base is less than 1, your graph will be decreasing. And it is, right? It's decreasing. It didn't ask for that, but it's good to talk about. We have one last example. We good so far? Okay? Doing okay? Okay. All right. Sorry, Remy? Question? All right. We're going to example 6. And this one has a lot going on in it. So this is our last one, and I only gave you one of these in your homework. So do this with me, and then you only have to do one of these in your homework. Then you have very short homework, and I'm going to do the first 3 with you. So you're going to get it done in class, especially if this third period has a few extra minutes added on. We are good. Okay, so in example 6, there are 4 things for us to do. Graph the given f of x, which is a log function, okay? Find the inverse, understand the language, that means inverse. Find the inverse algebraically. Then graph the inverse, and then analyze, which is answer all the questions. All right, let's start with f of x. We're not trying to make life hard and make an XY chart and all that stuff. Let's go to our graphing calculator. Okay, so everybody pick up your graphing calculator and go up to y equals and type this in. You put the 2 first, then math alpha math. And I like to see what it looks like, just so I have a visual in my head. Okay, so that's what my graph is supposed to look like. Now let's get the details by looking at the table. Okay, so you're going to go to the table and pick some nice points, right? Pick points that make you happy. How many to do? There's not really a rule about how many to do, guys. It's just you want to kind of be able to complete the shape. That's good enough for me. I can see where it's curving there, but I don't know what's happening over here. I mean, clearly, I got this end behavior of the graph, right? As x gets bigger, y gets bigger. I got that. But what's happening over here? Again, with logs only, by the way, you can see where your asymptote is very nicely. It's at -1. Why is it at -1 and not 0? Make a connection for tomorrow. What does x plus 1 in parentheses do to a graph? Moved it left 1. It moved it left 1. That's what happened there. It took our parent function and shifted it to the left 1. So it should make sense that we have an asymptote at -1. But your calculator told you that. It's right there. -1 is our error. So that means between 0 and -1, those numbers are getting smaller and smaller and smaller and going down forever. Okay? Now, let me see. I just want to label this nicely. I messed up last period. Okay. So this is f of x, right? That's what we just graphed. Now it tells us to find this algebraically in the graph. But when I did this earlier today, it was kind of hard to tell the difference between the 2 graphs. So let's actually analyze f of x now, and then we'll go back and do all of the inverse. So let's answer all these questions about f of x. Okay? All right, so what's the domain? -1 to infinity, perfect, right? Look at it. Look at your graph left, right. When do we start seeing points? Right after -1. And then all the points continue to the right. Good job, Zach. Range, all of them. Right, Evan, good. Okay? Now, look at our end behavior. The limit of f of x as the x values get bigger, the y values also get bigger, okay? Now look, this is not right. We can't go to -infinity. This is kind of a generic way of writing our end behavior, but sometimes if there's a vertical asymptote in a graph, we can't go all the way right or left, okay? So we have to fix this end statement. Limit of f of x as x approaches what? What is x approaching? -1. If we don't put a from the right or from the left, it by default means from both directions, and we can't get to our graph from the left. Remember, we can't cross that. So it's from the right. You have to put that, okay? Equals, and what are the y values doing as they get closer to that? Going decreasing, going down. Very good. Asymptote, if we write -1, we get it wrong. X equals -1. Just wanted to make a point. Okay? I need to know if it's a vertical or a horizontal line. It's wrong. You don't get any points for -1. You have to put X or Y. Vertical, VAX. Intercept, 0, 0. And concavity, concave down, right? Okay, done with f of x. Now let's tackle inverse. Again, know what that means. It doesn't say find the inverse. It says find f to the -1 of x. We know that means inverse. Algebraically, we have a function, switch the x's and y's, solve for y. We're not doing the example 5 right above, so I'm going to do that up here, okay? So remember, f of x means y, right? So here's my function. I'm going to switch x and y up here. So x equals 2 log base 2 of x plus 1. Guys, one of the things you have to be able to do in section 2.8 on your online quiz is be able to do the inverse algebraically in a table of values, in a graph, okay? These are the hardest, to have to do it algebraically, because any other situation, you just switch them. But here we switch, and then we still have to solve for, we still have to solve for y. Sorry about that. We have to solve for y. So go back to algebra 1, and because we had to switch the x and y. I forgot to switch it, right? I put 2 x's in there by accident. Sorry. Are they with me? So here's where we have to get y by itself. Now, y is locked in parentheses attached to a log that has a number in front. We can't just say, all right, just everybody go to the other side. We have to follow our algebra rules, okay? Anyone want to take a guess at what our first step would be? Yes. So she said divide by 2, and she's talking about this 2, by the way, right, Remy? Talking about that too? Yeah. Here's the thing. You want to isolate your log. We want the log and its base and whatever comes after it by itself. This 2 got to go. It's multiplied. This is 2 times the log. We're going to use our algebra 1 rules and divide both sides by 2. Okay? So what I have now is x over 2 equals log base 2 of y plus 1. Okay? If those parentheses weren't there, if it was just log base 2 of y plus 1, we would now then subtract 1 from both sides. But the parentheses means we're together, don't break us up, leave us alone, we're all one unit. So what we have here is the log is now isolated. Yesterday I taught you, so review of yesterday. Yesterday I taught you, you can't solve a log equation with the word log in it. You have to write it in its other form. And so don't let it throw you off. Everybody look, you always start with your base. It just happened to be that your base was on the other side yesterday. I don't know, I'm making this up. That's a good one, actually. Yesterday it looked like this. Remember we would do 2 to the x equals 4, 2 to the x equals 4. Okay, it's the same thing. Just always start with the base, go to the other side of the equation, equals whatever's left. So we have 2 to the power of x over 2 equals y plus 1. Remember, your goal is to get y by itself. There's one thing left to do, which is subtract what? Minus 1. Okay, here's how we write our answer. Right, there's the symbol for inverse, and I'm just rewriting this. 2 to the power of x over 2. 2 to the power of x over 2, and minus 1. Minus 1 is not in the exponent. It's on the ground with the 2, and you can't subtract the 2 and the 1. Somebody thought that you could. You can't. They're unlike terms. One has an exponent with a variable. They're not alike. You can't do 2 minus 1 or anything. It's it. 2 to the power of x over 2, minus 1. And that's algebraic. Okay? So we did that. Now we're going to graph it. Listen, you could take the time, and it's not wrong to do this. You could take the time to put that in your calculator, graph it, look at the table, pick points. Or you can do it a little faster by saying, oh, I know something, that I'm about to graph this guy's inverse. And if I graph the inverse, it means I just switch the x's and y's. So I can take these ordered pairs and flip them, because that's all the table of values is going to show me is those points flipped. That's what it's going to do. Okay? So, like, I have a point at 0, 0 for f of x. So when you flip 0, 0, you're still at 0, 0. This point is at 1, 2. You don't have to write it. I'm just making a point. This point is 1, 2. Flip it, I'd be at 2, 1. This point is 3, 4. Again, you don't have to write it. Flip it, I'd be at 4, 3. And let's do one more just to finish the shape of it. Remember, this is an exponential function. The inverse of a log is an exponential. It's making that j. This is 7, 6. If I flip it, I get 6. Every period I say I'm not going to write right there. I'm going to post it. Okay, so we can see what's happening. I know it's messy when you have two of them in the same graph. We can see that j, and we know it's going to keep going this way, but how far? Again, if you couldn't remember this, you could go to your calculator and use it, but here's a great thing. If we have a vertical asymptote at x equals -1, we just flip it in the inverse. Now we'll have a horizontal asymptote of y, flip the x and y, at y equals -1. And remember, our asymptote has to go on our graph, and then we can finish the graph. It's going to get as close as it can to that, and there's my HA of y equals -1. Graphed. Almost done. Let's analyze, and it might be easier to look at mine unless you're using it two different colors. So we're looking at the green graph now, green. What's that domain, y'all? All of them. All those numbers. Right? Goes to the left. Nothing is stopping those arrows left and right. How about up and down? We have a HA, so we're getting stopped down here. And Zach, let me ask you. So Zach said -1 to infinity. I'm going to ask you two questions, Zach. Am I going to put brackets or parentheses on the -1? Yes. And does it matter what order I put these two in? Yes. Okay. Least to greatest. Least. -1 to infinity, not including the -1. Okay. End behavior, as x goes to the right, look at the green graph. As we go to the right, y's are going infinity. To the left, this one's fine, right? This is totally fine. We are going to the left. Nothing stops it from going left, but something is stopping it from going down to -infinity, -1. We can't go past -1. It's a limit. It's limiting us. We already talked about this. Switch x and y. Oh, by the way, domain and range got switched too. Domains are x's, ranges are y's. See? Just flipped. Always happens in the inverse. Intercept, they share an intercept in this problem, right? 0, 0. And this one is concave up. Okay. You guys did a fabulous job. Fabulous. I'm going to do the first three problems with you, so just stay. I know you guys like to go get in your little huddles, talk about wrestling. But we're going to do the first three together. So please just stay put, and then I will set you free. The first couple of problems are finding inverses algebraically, and I just wanted to practice them with you, okay? So just say thank you and be okay with it. Okay, so number 3 gives you a log function, and all it does do is find the inverse. So just understand what the directions are saying. Take number 3, that's what's given, and find the inverse, okay? So you go inverse, that's switch x and y, and since it's an equation, we'll also solve for y. So I switch x and y. Here's what you're looking for. Is the log isolated? Is there anything on this side that I need to add or subtract or multiply to get the log by itself? No. This is log base 3 of y. That is one unit. We're ready to rewrite it in its other form. Base, power on the other side, equals whatever's left. So I have 3 to the power of x equals y. Did we solve for y? Yep, that's it. It was an easy one. Say it again. What? What is in green is what was given. Okay, that's what was given to me on the paper. Okay, then I switch the x and y. Then I solved. Okay, and just so you know, you'll see it written like this. Kind of weird to see the y have that inverse, but if this was called y, that's a way of saying the inverse of the y. Okay? Okay, number 4, that's what's written on your paper. Okay? We find the inverse, we switch x and y, solve for y. Okay, before we can solve for y, though, in logs, we have to make sure the log is by itself. There's no other numbers to clean up to move to the other side. And this is all 1 unit. Remember, though, if those parentheses weren't there, I would subtract 2 before I could start. Okay? And I don't see a base here. What is our base? 10. This is a known 10. If you want to write it, you can. You won't ever see it given to you, or typically won't. Right? 10 to the x equals y plus 2. 10 to the x equals y plus 2. Did we solve for y? Nope. What do we do? Minus 2. So my final answer, here's my inverse symbol, 10 to the x, and then minus 2. Be careful. I always see students put the minus 2 up in the exponent. It's not. It's 10 to the x, and then take 2 away from whatever 10 to the x is. That's just same level. I'll just do one more, and then I will be quiet. And the reason I wanted to get to 5 is there's something in it that some students could find challenging. There you are. So here's what's given. Switch x and y. And solve for y. Again, because of the parentheses, there's nothing here we need to clean up first. The log is isolated. So once we've established that, we know to do this. Did we solve for y? Not yet. What do we have to do? Divide by 2. Okay, so nothing seems tricky yet. You're probably like, what are you talking about? This is easy. It's right here that you could easily make a mistake if you're not careful. Okay? What we can't do is divide the 2's. You can't make this like 1 to the power of x. Okay? We don't know what x is. So it's this number, it could, like, if x was 3, this is really 8, right? 8 over 2 would be 4. Because of this unknown, we can't divide that. But we do know something about when you have like bases. What do you do when you divide? You keep your base, subtract your exponents. That's what we have here. We have like bases. Don't forget, that's a 1, right? Keep your base, subtract your exponents. And that's it. Oops, I put the F there. It's okay. Should have been a Y. All right. I left you one more of those to do. I actually have 3 problems left. Thank you for waiting. Number 7's the long one that makes you analyze all the stuff. Not too much, though. Jaden, did that help? Having that? Hey, I like it when a plan works. You don't? Even with the word problem yesterday? Logs are a way of expressing mathy stuff that the science people make confusing. So if you get a word problem,